So these rules for how Ethernet works, about knowing when it's time to go, knowing if somebody has talked while I'm talking, are defined in this acronym here, CSMA-CD. And CSMA-CD defines lots of things. For example, can I do half duplex or full duplex? If between me and somebody else on this wire, can we both talk at the same time, or can only one of us talk at once? Now, Ethernet was originally developed as half duplex, meaning only one person could talk at a time. And I'll show you in a little bit later, especially when we get into the world of bridging and switching, how that all of a sudden made it full duplex as a capability. So CSMA-CD, the CS stands for carrier sense, and then multiple access, collision detect. Okay? You will almost guaranteed get one or more questions testing your knowledge of CSMA-CD. So let's go over that on the whiteboard to make sure that you understand how this operates. Okay. Okay, so here I have, let's just make it simple, 3 devices, and we're going to say they're all connected to the same Ethernet cable. Okay. You know what? Actually, you know what? I'm going to draw this like it really would be, because we know in real life they're not all going to be connected to the physical same cable. They're going to be connected to some box, like a switch or a hub. Let's just make this a hub. Okay, I've got a 3-port hub, and I'm going to have my PCs connected to that. And let's just put some port numbers on these hubs here, on these ports, so that we can reference them. And let's put some names on our PCs. All right. So let's first of all start out with the MA portion of CSMA-CD. So let's start with the multiple access. Ethernet is called a multiple access medium simply by virtue of the fact that back when it was originally developed, you had one thick coaxial strand of cable and multiple devices were physically tapped into it. And so it was one cable that multiple devices could access, hence multiple access, the MA. Now, if PC A wants to transmit some data, okay, let's say that he wants to transmit these bits right here. The first thing he has to do is perform carrier sense. Now remember, on this wire, we're talking about a twisted pair cable that's got multiple wires inside of it twisted together. And some of the wires are being used for transmit, some of the wires are being used for receive. So when we're performing carrier sense, what PCA is really doing is he's listening to the wires that are defined as the receive wires, the wires that data would come in on. So in carrier sense, he's listening and trying to determine, is anybody talking? Is the wire free? Now, with Ethernet, there is a period of time you wait. When you're performing carrier sense, you always perform carrier sense for the exact same duration. It's called the interframe gap. CCNA, I don't even think the CCNP is ever going to expect you to know how long this is, but I'll tell you it's a period of microseconds. Microseconds. So we're talking millionths of a second here. So you wait for this defined interframe gap, which is a few microseconds. If somebody is talking, you just have to wait till they're done. If you wait during the interframe gap and during this whole time of a few microseconds, nobody says anything, it's quiet, then you can go. So that's carrier sense. Spending time in this interframe gap, just being quiet, listening to see if anyone's going to go. So you start transmitting. we go. Now, as you're transmitting, you say, I've got control over this wire. Nobody should have it but me. I have this. But Ethernet says there's a possibility that somebody could have transmitted at the same time as me. Like this guy, right here. Maybe he had some bits to send, like that. And when he waited during the interframe gap, he didn't hear anything. So these guys both started at exactly the same time. Well, eventually their frames are going to come into this hub here, and the hub's job, actually I probably should have done this in a different color. The hub's job is simply to take bits in and put bits out. Any bit that comes in a port on a hub, the hub just replicates that bit and sends it out all the other ports. So let's just take this here. So once this red frame comes in, the hub will replicate it and send it out here, and he'll send it out here. Now once these bits collide right here, that is called a collision. That's a collision. The green frame and the red frame are now meaningless. Well, the way that PCA detects that, now this is the collision detect, is that while you're transmitting on your transmit pins, you're still listening on your receive pin. And the rules of Ethernet say, while I'm transmitting, I should not hear anything on my receive pin. If I do, I've just detected a collision. So that's how we've detected collisions. Now, what does Ethernet do about it? In this particular case, A may have only gotten 10% of his frame transmitted, or maybe 30% of his frame transmitted. It doesn't even matter. Maybe even 98% of his frame transmitted. Doesn't matter. If he detects a collision before this frame is completely gone, he says, uh-oh, this frame is bad. And so then he transmits something called a jam signal. And actually, both these guys would transmit jam signals because the green frame might actually make it over here as well, which would cause a collision detection event on C as well. But basically, he's going to send a jam signal, and the jam signal basically says, hey, everybody, whoever's talking, need to be quiet, we've just had a problem. So jam signal is basically a way of resetting the wire, making everybody be quiet. Now, a couple more things about Ethernet. When a station's transmitting and it detects a collision and it sends this jam signal, it does have the opportunity to try to retransmit again, but it's going to wait. After transmitting a jam signal, the Ethernet station will go through something called a random backoff. A random backoff. Now here's the theory. Both A and C, because they were transmitting at the time the collision happens, both of them will go through a random backoff. In theory, so this is a random timer that started. Chances are their timer should not be the same. Theoretically, they could be, but they probably will not. And so if C's timer counts down to 0 and expires first, he gets to retransmit his frame, and then when he's done, A can go. Now, if your frame, now we start seeing here some problems as to why you don't want to have too many devices on one Ethernet segment. If I have too many devices on one Ethernet segment, now I've got a couple of problems. Number one, every time I want to transmit my frame, remember, what do I do first? I do carrier sense. I listen for that interframe gap. Well, if I've got hundreds of devices on the same Ethernet wire, what's that going to mean for me? That means every time I'm listening, it's always busy. Oh man, I can't ever put my frame on the wire because it's always busy. I keep performing carrier sense and it's always busy, always busy, always busy. Similarly, maybe I say, oh, I got lucky. Here's a free slot. I waited and nobody's talking, so I start transmitting and oh, there's a collision. Because the more devices you have on an Ethernet segment, the more devices you have in your collision domain, and this is one giant collision domain right here, the higher the probability the collisions will occur, and you'll have to retransmit again. And every time you have to retransmit, that random backoff timer gets bigger and bigger and bigger. It gets longer and longer and longer. Now, another thing you should know. Ethernet is not going to keep trying and trying and trying forever. if you try to put it, if Ethernet's performing carrier sense and he says, okay, I'd like to put this frame on the wire, oh, it's busy. Okay, how about now? Oh, it's busy. How about now? Oh, it's busy. Ethernet will try up to 16 times, and then it will give up. It'll just silently discard that frame, say, I give up. Same thing with collisions. If I'm putting a frame on the wire, and every time I put this frame on the wire, it's always colliding with someone else, after 16 attempts, I will give up and say, game over, I'm finished. At that point, it's up to something at the higher level of the OSI model, maybe TCP or something at the application layer, to detect that that frame never got to its destination, and the higher level protocol will have to recreate that frame and start the whole process all over again by sending it down to Ethernet. So that is how CSMA-CD works, the carrier sense, the multiple access, and the collision detect. And Joe asks, what's the difference between FCS and CRC? So FCS is the name of the field at the end of an Ethernet frame that does error checking. CRC technically is the name of the, there's another field called CRC, but that's at like layer 3 and layer 4. So when you add a layer 3 header, for example, an IP header to data, IP does its own error checking, and the name of its field is called a CRC or a checksum. Layer 4 also does the same thing. I'm not sure if the actual algorithms that are used to compute the results are the same between an FCS and a CRC, but you will never need to know that for the CCNA anyway. You should just know that FCS is technically at layer 2, that's the layer 2 trailer, and CRCs are done higher than that, like layer 3 and above. Someone's also asking, do we need to know the pinouts for 10 base T, 100 base T, and 1000 base T? Good gosh, no. No, you don't need to know the pinouts for that, at least not for any certification test. You know, maybe if you're making your own cables and stuff, but you don't need to know the pinouts for those. David also mentioned that CRC is the math, so I guess CRC is the name of the algorithm behind it. But yeah, don't have to worry about pinouts. And I'll talk a little bit just coming up about, some of you might be wondering, what is he talking about 10 base T, 100 base T, 1000 base Ts? What is that? We'll go over those acronyms, and I'll mention what those are.